Let's discuss system today. What is system in signals and systems? We are studying signals and systems. So what is a system? In signals and system, we have so many definitions for system. But in signals and systems, in our course of study, system is defined as a process, or I shouldn't say defined, it can be viewed as a process that does transformation. Transformation of what? Transformation of an input signal into an output signal that is very different from the input signal. So what it does is, let this be a system. It means that we have an input signal, let's say X. The system transforms this input signal into another signal that is called our output signal. So system is considered as a process, or this process causes the system to respond in such a way that an input signal is transformed into another signal that is called the output signal. Clear? Now, we have two types of signals, continuous time and discrete time. Similarly, we'll have two types of systems. One which is continuous time system and second which is discrete time system. What is a continuous time system? See, if our input signal is continuous and the system responds in such a way that we get continuous time output signal, it is called a continuous time system. Clear? We have input signal, that is continuous time signal, and we have output signal which is continuous time signal. So that type of system is called continuous time signal. And if we have a system in which we have discrete input and the system results in transforming this input discrete time signal into a discrete time output signal, this is called a discrete time system. Very simple. So this is the basic definition of system. Then we have interconnection of systems. How are systems connected? There are several ways, because we don't have standalone systems. We have several systems interconnected to form a larger set of systems that actually performs some real-time work. Okay. For example, if you have a music system, there are so many systems inside that system that actually transforms the input. So let's consider a music system. Let's consider a music system. Even at its basic level, if you talk of basic level, what you expect? You expect, let's say we have a CD based system. So we'll insert this CD into the system. So we'll have first of all a mechanical system to cater to this. CD enters into the system, we are able to exit the CD. Then we have reading device. For example, we have devices to read the whatever is written in the CD. So there is a system which is reading device. Then it creates certain signal. Let's say this is first signal. Let's say this is a continuous time signal. Now, but when we are considering a CD, it will be a digital signal. So we have a digital signal here, discrete signal coming out of this reading device. Then you have an amplifier that will amplify it. Then you might have frequency synthesizer, so that you are able to select and deselect certain frequencies based on your taste. Then you may have some power amplifier to match it to the load, a large speaker. So there are several systems. These all are systems. So in a practical real-time application, practical application, we have systems that have several systems interconnected inside it, or a set of several interconnected systems constitute a real practical system. So they can be connected in series, that is called cascaded series connection, like this. System 1, let this be system 1. It is connected to system 2, and then we have the output. So this is a series connection. System 1 connected to the output. Input is coming to this system 1. Output of this, if this is x1t, is fed into the input of the second system, and then final output, we receive the final output. This is called cascaded series connection. Okay. Then we can have systems which are connected in parallel, like this is system 1 and this is system 2. They are connected in parallel. So this is a parallel system. We can have parallel plus series. We can have a third system in series to this output. So these are the different possibilities that systems are interconnected. Then we have feedback systems. For example, we can have feedback system. Input is coming to this part, then going to system, then it is the output, and from output what we can do, we can have a feedback system which is interconnected to the input. This is feedback system. This is the this is system 1. It can be an amplifier and this can be a feedback network. So this is called system in feedback, system with feedback. So these are the different possibilities with which we can have systems. Okay, so when the basics of system is clear, let's understand certain properties of system. But before that, let's understand what we are saying a system is. A very simple example. You know this is V, let's say Vs. This is source, this is resistor, and this is capacitor. Okay, let this be R, this be C. This is basically Vc. Let the current be I. Okay, so you can say IT is what? It is Vs minus Vc by R. This voltage minus this voltage by R. And since this is a capacitor, we know IT, this current will be equal to C. If capacitance of the capacitor is C, this will be C dVc by dt. So we can put it here, that is C RC dVc by dt is equal to Vs minus Vc. Okay, let's put Vc at one place. So we can write like this, RC dVc by dt plus Vc is equal to Vs. Now see, Vc is, we can take this as input, this is input Vs, and this is output. So we have a relation between input and output. So we can say that this is a system in which our input is this Vs and the output is Vc, and we have this system, continuous time system, that is actually transforming this signal into this signal with this function. So this is the process that is being done by the system over this input signal. This is the meaning of system. Okay, so now we see the first property of system. Altogether we'll see 6 different properties of a system. First property is whether a system is with memory or is the system memoryless. This is the first property. See, if first of all we consider memoryless system. If the output of a system, I'm giving you the definition, if the output of a system at any time, let's say t, is dependent only on the input signal at that time, that is, let's say with some, it is dependent on this only, or in case of discrete signal, xn results in yn. Here we can represent like xt results in yt. That is, the output signal is not dependent on any signal, on any previous signal, any previous input signal. That is t minus t1, t minus t2, it is not dependent on any other signal. If this was our, let's say this is our input signal. So at t equal to t1, whatever be the value of this, our output is dependent on this only, that is y at t1 is dependent on x at t1 only. It is not dependent on x at 0 or x at this point or this point. It is dependent on this point only. Then it is called memoryless system. For example, we have a resistive network. Let's say this is V, this is R. So I is what? I is basically V by R. So whatever be, if V is your input, whatever be input at any time, output will be dependent on that only. In this resistive network, it has nothing to do, if this is, let's say this is a AC circuit. So I will be Vs by R only. It will depend on that instantaneous value of voltage only, nothing else. So this type of system is memoryless. Second is system with memory. So similar to this definition, a system which has memory is a system which is dependent on the value of the input signal at that moment, and at other values of input signals also. That is before that. That is, if the output is dependent, if this is input and this is your T1, if the value of output is dependent from 0 to T1 of this, that is y at T1 is dependent on, let's say, from t equal to 0 to T1 of xt. If this is the case, that is, it is not dependent only on this point, it is dependent how the signal went from this to this. That system is with memory. It is called a system with memory. Okay. For example, a very simple example. We just saw capacitor circuit, RC circuit. This one, V, Vs, R, C. What is the, I is C dV C by dt. So if you want to see what is Vc, what it will be? It is minus infinity to t I 1 by C I dt. So it is not dependent on the value of the current at time t. It is dependent on the value of the time from minus infinity to t. This type of system is having a memory. Okay. Similarly, for discrete systems, if we have a yn like this, it is xn plus xn minus 1 or n minus 2. Then it is dependent on two signals, signal at n and signal at n minus 1. So this type of system has memory. So this is the first property of a system, that it may have memory or it may be memoryless. Okay. The second property of a system is called invertibility. What is invertibility? Invertibility of a system. Invertibility. It means a system has an invertible system also, so that the original signal can be retrieved back. That is, if we have xt entering this system S giving output yt, then we should have a system invertible of this, where when we put yt, we are able to retrieve back xt. This is the meaning of invertibility. In case of continuous time, it is t. In discrete, this is n. So you'll think, why we'll need this? If we have transformed a signal into another signal, why do we need to have the system, the original signal back? There's no logic to it, because we have, for some reason, we have transformed a signal to this. Why we would like to have invertible system of that? It is required, and it is required more often than you think. Very simple example is your communication system. Communication system. What you do in a communication system, whether it be continuous time or discrete time signal, what you do? You have a message, that is the input signal. Your message is your input signal. Okay. So you have a big system. First of all, what you do? The first process is, when you have an input signal, you actually modulate it. Okay. Then you send it through a channel. I'm giving a very simple diagrammatic explanation to this. Modulation, then channel, then you receive it. Okay. After modulation, what you do? You transmit. You transmit through the channel. Then you receive. And when you receive the channel, you demodulate it. Okay. And then you have the signal back. If your signal was xt, it is xt again. This was xt, you modulated. You have a system. When you change xt to, let's say, yt, then you changed your yt signal you went from this point to this point. From transmitter, it went up to the receiver. That is, maybe an antenna was a transmitter, then through air it reached the receiver antenna. So here you receive it. Then you have a system which is invertible of this. This is the property of invertibility. So the process is reversed. Modulation. Now here what you do? You demodulate and you retrieve back your signal. So this is the property of a signal to recreate an original signal from the output signal. Okay. Third property of a system is called causality. We say a system is causal when it depends on, when the output signal depends on the value of the present input signal and input signals up to that time. That is, we just saw, let me write it, causality. We just saw, what was this? Vc was 1 by C, then you have minus infinity to t I dt. So up to t, from here, from minus infinity to t. So if we have such a system, we say the system is causal. Otherwise, it is not a causal system. Okay. A corollary to it will be, it does not anticipate future values of the signal. That is, you cannot say that yt is dependent on xt. When the system is causal, you say yt is dependent on xt and xt minus 1. This is a causal system. It is dependent on present signal and previous signal. But you cannot say yxt plus 1. That is, in the next moment, what the value of the input will be. You cannot have anticipation. That is not a causal system. Okay, we have non-causal systems where we anticipate the future values of the input signal, and based on that we have feedback type of system where we try to check our output signal. But that is not a causal system. A causal system, is a system which depends on its present value and its earlier values of the input signal. The fourth property of a system is called stability. It is one of the most important properties of a system. What is the meaning? Its meaning is, what is the meaning of stability of system? If the input signal is bounded, what is the meaning of bounded signal? That is, if we have a signal xt like t, so xt plus 1 will be t plus 1. It cannot be 1000 t. So this is bounded. That is, with small increase, the signal does not diverges. So that type of signal is called bounded signal. That is, with small increase, you have small increase in the output also. So if the input signal is bounded, the output system is also bounded. This is the meaning of stability. Let's understand it. For example, I am rubbing it. Let's say this is R, this is V. So I will be I is V by R. So if you have 10% increase in V, you'll have 10% increase in I. For a 10% increase in V, you cannot have 100,000% increase in I. So the system is stable. Or if a car is moving on a road, if you increase the acceleration by 10%, let's say, then velocity should increase by 5 to 15% or some bounded value. Why this is bounded? Because you have a friction force here which is acting on the body. When acceleration is increased, it does not mean if you increase the acceleration by 10%, your speed will go from 40 to 4000 kilometers per hour. It won't go. Why? Because the system is bounded by frictional force. If this force was not there, the system would have been unbounded. So stability is a must. Whenever we have a system, we try to achieve stability. With respect to different aspects. For example, if let's say this is your Vs, this is R, and this is C. You know the value of I. You know I is equal to C dVc by dt. Okay. Stable means once you give I1, let's say the Vc is Vc1. Then tomorrow also when you give I1, it should be Vc1 only. Third day also for I1, it should be Vc1 only. It should not change. It should not change with time. It should not change with temperature. Or even if it changes, that should be bounded within limits. What I am trying to say is, if today's temperature is 20 degrees Celsius and you have Vc1 for this, tomorrow if the temperature is 25 degrees Celsius, the change in Vc, if this is Vc1 dash, if the change in Vc should be very, approximately equal to 0, very low quantity. It should not be very high. For example, for I1, if this was 1 volt at 25 degrees Celsius, then at 20 degrees Celsius for I1, it should not go to 100 amperes. It should be 1.1 or 1.05 amperes. So that is the meaning of stability. That should be stable with respect to time, with respect to temperature, and with respect to other parameters that is surrounding the system. Now the fifth property is called time invariance. Time invariance. You must be hearing of the term linear time invariant system. So this is time invariance. It may seem that the characteristics should not change with time. That is actually stability. Time invariance means that if for xt, if the output is yt, then for xt minus t0, your output should be yt minus t0. That is, the property should shift. If there is a shift in time in the input, the output should also shift by that property, that only. That is, if this is your xt, for which your output was, let's say this. Let's say this is your output. Then if you have the input like this, then your output should be like this also only. Okay, this is the meaning of time invariance, that if yt is for xt, then yt minus t0 for xt minus t0. Similarly, for if xn results in yn, xn minus n should result in this. This is the meaning of time invariance in signals and systems. Okay, don't think time invariance means that with changing time the system stability should be maintained. Time invariance means this. Okay, and finally we'll see the sixth property, that is linearity of a system. So that finally we'll understand what is linear, time invariant, causal, stable system. So linearity. So what is a linear system? Linear system is a system which possesses the property of superposition. And what it is? First, the property of superposition means first additive. That is, if yt1 was in response to xt1 and yt2 was in response to xt2, okay, input and output, then additive property means if we feed the system with xt1 plus xt2, our output should be yt1 plus yt2. That is, if the input signal is weighted sum of some signals, the output should be the weighted sum of response of those input signals. xt1, xt2 should result in yt1 plus yt2. Okay, discrete also nothing, xn1, xn2, yn. If we feed this with xn1 plus xn2, we should get yn1 plus yn2. Okay, this is the additive property. And the second property is called scaling property. Second property of linearity is scaling property. What it is? If xt1 results in yt1, then a into xt1 should result in a into yt1. This is, if the input signal has been scaled up by multiplying factor of a, the output signal should also be multiplied by that factor a. This is scaling. So if a signal possesses these two properties, first was additive and second was scaling. So if a system possesses these two properties, we say the system is linear. A very simple example will be this R. Let's say this is R, this is V. So our current will be V by R. If our new voltage is, let's say, V1 plus V2, then your current will be V1 plus V2 by R. So the additive property is there. If we have multiplied this by, let's say, K, we have a voltage that is kV, our output will be kV by R. So this system possesses linearity. This system is linear. Okay, this is clear. We'll see some examples and then we'll understand this. Let's say we have a system. Let's say we have a system where yt is equal to t xt. Let's see whether it is linear or not. We know y1t will be tx1t and y2t will be tx2t. Let's say we have third signal x3, which is a combination of these two input signal, ax1t plus bx2t. You remember how we express linear dependence of systems? So a and b are certain scalars. So we have a signal x3t, and that is this. What will be the value of y3t? Y3t from here will be tx3t. So this is atx1t plus btx2t. Now you can see this and this. This is equal to, we can say, a into y1t. This is y1t plus b into y2t. So for another signal, the output is clearly defines the input signal. That is, this is a linear system. You can see x3 y3t is exactly what we have in the defining expression. So this is a linear system. Okay, but what if our signal was this? Let's say x square t. Then y1t will be equal to x1 square t, and y2t will be x2 square t. Now similar to that, let's have x3t, which is x1t plus b x2t. Okay, so ideally we should have y3t equal to x3 square t. Let's see whether we get x3 square t or not. y3t will be equal to x3. See, this is okay. Okay, we should get our result should be a into y1t plus b into y2t. Then we'll say it is linear. Let's see, this is this x3 square t, that is this square plus this square, that is a square x1 square t plus b square x2 square t plus twice ab x1t x2t. Okay, this you can see is y1t. So this is a square y1t plus b square y2t plus twice ab x1t into x2t. Now you can see these are scalars, so a square b square is not very significant. We can say k1 and k2. If this was linear, then this should have been up to this only. If this was up to this, we would have said that the system is linear, but we have another term. So the system is not linear. The first we discussed txt, that was a linear system, but x square t is not a linear system. So I think you understand what is a linear system and what is a non-linear system. So we have discussed 6 different properties of a system. These are for basic understandings. When we'll get deeper into linear time invariant systems, things will be more clear to you. Okay.